Good afternoon, everybody. How was your lunch?
Was good, Professor.
So in this afternoon, we will continue our desalination plant design and then some of the basic information. So far, everything is okay. Do you have any question? Or do you have any other comments that you want to share with us? Is it okay, everybody?
Yes, it's okay.
All right. A second, my So we will continue out of brine. So out of brine, we have connected with this pressure exchanger to save the energy. With out of brine can be connected with the brine mining. So this is the one of the example of this brine mining. So in seawater, there are a lot of valuable materials. So you can see the sodium and potassium chloride, magnesium, calcium sulfate, and rubidium, lithium, vanadium, the boron, was molybdenum. So when you have your brine, so you can select with the multivalent ions and the monovalent ions using some of the nanofiltration process, and this can be collected with calcium precipitation using sodium carbonate to produce the calcium carbonate, and then divalent ion which can be rejected from nanofiltration membrane. So monovalent can pass through. So monovalent can pass through this one. And then you have also very much concentrated multivalent, the magnesium hydroxide, and some of the water can be produced. And you have also metal extraction and lithium, so sodium hydroxide. So based on your seawater brine management, and then we can have a lot of the useful material, and then we can also resell this kind of compound. For example, this is the seawater concentration, and this is the price, how much it cost. For example, like the rubidium chloride, this costs around $10,000. So that you can utilize this kind of compound from seawater brine, and then 1 kilogram you can resell for $10,000 of your value. Also, lithium carbonate, around $12 or $20 for 1 kilogram. Also magnesium, $10, bromine, and some of the compounds, sodium chloride, even table salt, calcium sulfate, calcium carbonate. So we can get a lot of the valuable material, which is a very high cost. So from the brine, if we selectively collect this material, so you can be a very rich person to have this technology. So that's the how we can develop the brine mining from seawater and RO process because they just discharge. Also shutdown and the restart of the Sydney desalination plant. Already this is the one of the assignment question. So with the dam storage reaching 90%, the minister directed the desalination plant to cease production July 2012, and dam storage levels fell below 60%, 27 January, and the city desalination commenced restart. And desalination plant started delivering water to Sydney water network in March 2019 and reached the full capacity in August 2019. The immense restart period ended on 27 September 2019 because of the very heavy rainfall. So in 2020, during the pandemic period, the heavy rainfall stopped all the plant operation, except just the minimum operation of the desalination plant. So this desalination plant revised operator license will take effect from 1st July 2023 and recognize that the plant has always been and will continue to be an essential component of the Sydney water management and an integral city of our city water resilient future. So that's the you can mention about detail in your assignment that you must also cover from July 2023. So we will continue to operate the Sydney desalination plant. So this is our sixth desalination plant. What's their TDS concentration? What's the difference capacity and RO configuration? BWRO second plus, and the RO recovery 45%, and BWRO 90%. And you have a pressure exchanger or dual works energy recovery device. So 3 of them utilizing pressure exchanger, 3 of them DWEER, dual work exchanger energy recovery system. So you can see how much energy they utilize for total. And then this is only RO reverse osmosis high pressure pump, so that you can get some overall picture of the Australia SWR desalination plant. So when you have your assignment, so you can try to consider which process diagram is the best, and which kind of energy cost you can follow, then how you can make a better design. So you can refer to all the basic process of the desalination. So you can combine. So initially, I told you have a different plant has a different technology, which one has very low desalination energy consumption, then how this can be connected each other, so that you will consider based on our lecture note, and this is the less energy consumption, this has a process like this, so that you want to design your process based on this kind of material. So that will be a very good justification why you select this process, why this process is the best based on your experience and then your information. So that will be a very strong your assignment 3. So that's the basic concept of the seawater desalination plant design. So now we can go for a little bit more detail parameters for design of the RO plant. And then we consider as a manual method, also software program method. So we will try because you need to understand the concept first. So this is the plant capacity. This plant capacity has, we have several, thousand cubic meter per day. And then you need to have this information. Also, feed water quality, you need to have TDS. So what's your concentration of the dissolved salt concentration to calculate your osmotic pressure pi. And then you need to have also membrane properties. So this membrane property will be provided by the manufacturers. So what's the element? How many average permeable flux? How many salt rejection rate? It will be produced. So you will get this one just from your manufacturing of the membrane company. Also operating condition, how much feed flow rate, how much recovery rate do we need? So we will have this kind of operating condition. So let's have basic auto design by manual calculation. As a one example. So let's say you want to design 300 cubic meter per day. So you can use the wave to size the auto feed pump for one tray. So what condition to use? Calculate number of pressure vessels, element of pressure vessel, and total number of element. So this is the basic example of the water reuse. So your assignment is more about seawater desalination, and this is the more wastewater reuse example. But basically, they are same. Just a matter of you have a less concentration of the TDS in your example. So we want to use the brackish water because this is the wastewater we use. The BW30, 400 membrane, feed water, secondary switch effluent, TDS is 1800 ppm, the water temperature 25 degree, and we will have also production cost 300 cubic meter. So we will make one squeeder, one unit to combine all the 300 cubic meter per day, or we can separate. So we can use reverse osmosis system analysis. So this is the basic steps. Step 1 to 10. So we want to use as a manual. So by your hands, you can calculate this kind of information. But if you have a very big size, like a Sydney desalination plant, you need to design 250 billion liter per day. So we can utilize the wave software. But this kind of very small size, 300 cubic meter per day, we can utilize the basic hands, like what's the step 1? Consider feed source, feed quality, feed the product flow, and require the product quality. And step 2, select the flow configuration and number of passes. Step 3, select the membrane element types. Step 4, select average membrane flux. Step 5, calculate the number of elements needed. Step 6, calculate number of pressure vessels needed. Step 7, select number of stages. Step 8, select the staging ratio. Step 9, balance the permeate flow rate. So we have a 10 step. So we go for one by one to design your RO plan. And then this will make a very good indication how you start. Because most of people, when they ask you to design, but they don't know where you to start. But this is like a good exercise. You can start with 1, 2, 3, 4, 5, and then you will be very clear what to calculate, how you can get the more confident to mm, design of your calculation. So your assignment also same, you have to calculate step 1, how many vessel, how many element, how many array, how many stage, how many parts. That sort of thing will be all related to this step 1 to 10. So let's say you want to design your RO plan. So consider first the feed source, feed quality, feed flow, require quality product. So membrane system design depends on the available feed water and the application. The system design information and the feed water analysis should be collected first. So you need to collect your water quality. Especially, you need to be careful feed water source for what's the SDI. And then you choose the overall feed water concentration, what's the osmotic pressure or specific ion. So you can send the sample to analytical center to measure different ion for your water, and you will get the specific ion. Otherwise, you can have a very rough estimation of TDS that you can get the osmotic pressure roughly, and the individual ion from water analysis is always preferable. So what's the SDI? SDI less than 3. SDI less than 5 in terms of well water and the surface water. So I will show you what's the SDI value. Yeah, this is the SDI. So we just say silt density index. What's the silt density index? SDI is calculate number based on filtration of a sample through 0.45 micrometer pad. SDI readings are used to indicate fouling tendency of a water for use as RO feed water. The RO feed water, as you can be seen in the video, so you have a very, very narrow space of your seawater channels. So if you have a very heavy object, and then your RO will be completely clogged, which means you cannot make any filtration because your water is too dirty, and then you cannot pass through your water in the RO element. So that the SDI is indicated. So you have water, your feed water, then you pressurize. You have a 0.45 microfilter here. There you can pass through. So if you have a lot of particle, then your SDI is very high. So if you have a very clean water, so your SDI is very low. So what they are indicating is this is equation. SDI 50 minutes is equal to 100 or minus T1, T2. So T1 is time in seconds to filter initial. So initially, let them collect 500 millimeter of sample. And then after 15 minutes later, T2. T2 is the in second filter final 500 millimeter. How many hours, how many minutes, how many seconds you spend. So based on this one, you will collect STI 15. So STI 15 is the one of the uh, indicator. So you have a more clean water. Your STI 15 is a very low value, less than 5. But if you have a very dirty water in your feed water, this will clog your RO membrane channel. So you will have a very, very big problem for operation. So SDI 15, you have to be less than 5, this value. So which means less than 5 will give a good number to filter your reverse osmosis membrane. So in this situation, every manufacturing auto company, they want to see SDI. At least you have to make sure clean pre-treatment. Otherwise, you damage your RO and you cannot make a warranty. So when they decide warranty timing, the SDI is the one of the indicator to make sure your RO membrane warranty is 2 years, 3 years when you have SDI less than 5, less than 3, less than 1. So that we recommend. So if you see as the water quality, you need to see in your SDI. So step 1, you want to get the SDI value. You want to get your feed water concentration of osmotic pressure as well as individual component. So you can collect this data and then go step 2. Step 2 is flow configuration and number of passes. The standard flow configuration for a membrane system is plug flow. So you have an element, the water is flowing from right to left through the arrow element channel where the feed volume is passed through the system. So only once this feed water pass through in your flow system, it's not like recirculating or re-rotating your uh, feed water. It's only one pass. And then our system is usually designed for continuous operation and the operating conditions of every membrane element in the plant are constant with time. So a permeate stage system is the combination of the two conventional RO system where the permeate of the first system becomes the feed for the second system. So that's the how you can also number of pass, number of configuration. Normally we just put the flow, and then you need to go through double pass because as you discussed during the Sydney desalination plant, most of plant they need to have a second pass because of boron or bromide concentration. So you can have a second pass for your seawater desalination. So we decide plug flow and second pass system. And you need to decide membrane and element type. The elements are selected according to feedwater salinity, feedwater fouling tendency, and required rejection and energy requirement. The standard element size for a system greater than 2.3 cubic meter per hour is 8 inch in diameter and 40 inch long. The smaller elements are available for smaller system. For high quality water applications where the very low product salinity is required, the ion exchange reagents are frequently used to polish our permeate. If you see the membrane type, TW, BW, SW, SWHR, nanofiltration. So they have their own different application of the feed water TDS. The total dissolved solid less than 5,000 ppm, 1,000 ppm, 5,000 ppm. The seawater 3,000 to 15,000 ppm. Seawater high rejection, HL means high rejection, 10,000 to 15,000 ppm. Nanofiltration is less than 1,000 ppm. So based on your feed water TDS, you can select PW or SW, HL. So they have two different types of 4-inch, 8-inch. So 4-inch, 8-inch different type. Then permeate quality, you will have less than 50 ppm, was less than seawater desalination, 150 ppm. Then this one is Paris, less than 500 ppm. So based on your experience or based on your membrane manufacturing company suggestion, so you need to decide. So you need to decide the membrane, which membrane is the best application. So in your assignment, so you need to go seawater. So seawater HL or seawater membrane type, you can select from your membrane element. So this will be given by your software. So we will have a discussion after this step 3 and step 4 and different steps. So this is step 4. After you select your element, so you can select average membrane flux, design flux. The RO systems are usually designed for a specific permeate flow rate and a specific system recovery. These numbers and the specific feed water source are the information required to estimate the number of membrane elements, pressure buses, and stages. To select the design flux in terms of gallon per flux, the feed flux, or LMH. So per day, the G and then square feet and day, GFD or LMH, liter per square meter hour, based on pilot data, customer experience, or the typical design fluxes according to the feed source from membrane system design guideline. So step 4, we focus on average membrane flux so that you can estimate element number, pressure vessel number, stage number. So that's the reason we need to make sure average membrane flux. This can be given by the manufacturer because whatever you select from element, you will have a recommended average water membrane flux. So you can say that seawater has around 30 RMH, 20 RMH based on this element. So you can get this result also from experience or from the manufacturing company. So you select the average membrane flux and number of elements. So the total number of elements needed is equal to design permeate flow rate. So let's say 300 cubic meter per day. That's the design permeate flow rate. And this is design water flux and active membrane surface layer of the selected element. So we can get the information from the manufacturing company. Dow, Piptech, PW30 400 element has 37.2 square meter of active layer. So this is the 37.2. Design flux is around, they recommend, let's say, 30 LMH. And design water permeate flow rate is around the 300 cubic meter per day based on our design capacity. So total number of elements you can get from this step 5. After step 5, if you know what's the pressure element, and then you can get how many pressure vessels needed. So number of the total pressure vessel is equal to total number of elements. Already we got from steps 5 and number of elements in pressure vessel. So in pressure vessel, we can put maybe 7 or 6. Then we have around the element, the 12, and then you can say that how many number of pressure vessel required based on your total number of element. Also round up to the nearest integer, and for the largest system, 6-element buses are standard, but buses with up to 8 elements available. For smaller and compact systems, shorter buses may be selected. Although the approach described in the following sections apply for all systems, it is especially applicable for 8-inch systems with a larger number of elements and pressure buses, which can be arranged in a certain way. The small system with only one or a few elements are mostly designed with the elements in series of the concentrated circulation for maintaining appropriate flow rate through the feed and brine channel. So based on the step 6, you will get how many pressure vessels you need for your design water flux. After that, step 7 is the staging. So you have a different water quality, brackish water and seawater. In terms of different recovery rate, 60%, 80%, 90%. This is seawater, 40%, 45%, 50%, 60%. So based on your water quality, your recovery, you can decide how many number of element position you have, and then how many you need to follow the staging, 1, 2, 3 stages. So this is what's your current position of your element stage and brackish water. You will look at it's like a steady desalination plant. You want to recover 45 to 50%. So which means you need the number of serial element position is 7 to 12. Then you need a stage around 2. 2 stages you have to design. If it's a 7-element vessel, also 1 or 2, you can design. Also, you can have a number of stage 8 into 1, 1. So based on your assignment, you can design steady desalination plan. And in terms of the quality, also you can design for 50%, maybe 6-element to 2 stage or 7-element 2 stage. So you can fix this stage of your seawater desalination plant. And you have to decide the array ratio. So you have already how many elements you need, how many pressure vessels you need. If you know how many pressure vessels, you can also select array ratio. The array ratio is important to recover more. So if you have a system with the 4 buses in the first stage and 2 buses in the second stage, the staging ratio is 2 to 1. A 3-stage system with 4, 3, and 2 buses in the first, second, third stage, respectively, has a staging ratio of the 4:3:2. In brackish water system, staging ratio between 2 subsequent stages are usually close to 2 to 1 for 6-element vessel and less than that for shorter vessels. In 2-stage seawater system with 6-element vessel, the typical staging ratio is 3 to 2. So you can possibly designed for your seawater desalination as a two-stage, as a 3 to 2 staging ratio to achieve your water recovery around the 50%. So that's the how you can get your uh, staging ratio. So based on this step A, then we can go balance. So this balance also you can be calculate from your hands as well as your software. So how the system recovery, feed water salinity, low pressure membrane, high water temperature, new membrane. How this can make a balance of the permeate or concentrate flow rate. So, considering all the aspects so that we can utilize the wave software to make a balance rather than calculating by hand. So this is the example. You remember the initially, okay, let's say we want to have a brackish water, surface water quality SDI less than 5, and then required permeate flow is 720 cubic meter per day. And this is 6 element pressure vessel we want to use and 75 recovery ratio. So let's go for step 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we go one by one. What's the flow rate? What's the quality? The SDI is less than 5 because of surface supply water. The total volume is 720 cubic meter per day. So we will go for plug flow system. Also membrane, we like to have a BW30. The BW element with the active membrane rate is area is 33.9 square meter. The recommended average flux for surface supply water feed with SDI less than 5 is almost 25 LMH. So this is the given by this manufacturing company. Also, this is already, you can purchase your membrane element. So that this is also given by the manufacturing company. Based on that, based on this information, we start calculate element. So 700, our design permeate flow, and then this is the 41 0.67 liter per hour, and this is 33.9 square meter of membrane surface and 25 LMH for average flux, which means we need the 37 element. Then this 37 element, 6 element pressure vessel. We need to put every pressure vessel 6. So which means 5.8. So we will get the 6 pressure vessels. So 6 pressure vessel, number of stages, 6 can 75% recovery. So we can have a two stages because of this information, and staging ratio selected 2 to 1. So brackish water staging, we have a 6 element. So 2 to 1 means 4 to 6. Appropriate staging ratio can be collected. So this is the how we can get the your staging and appropriate staging ratio. So that's the we can calculate using our hands, using the 10 steps. However,
Okay.
if yeah,
Just what's the 41.67?
this one, this is the unit conversion.
Oh, okay.
Yeah, this is cubic meter per day. So you convert to 41.67 liter per hour.
Professor,
Yeah.
why does it have to be 2 stages?
Why? Because you have a 75% recovery. Yep. And then you have the brackish water. So if you go back to our step 7, what's the stage selection? So you are saying, okay, we have a brackish water, 75% recovery, And then 2 stages, 6 element battery is the ideal. So this is the table you can use, but of course, you can try to also ask some people already operational, because even brackish water has a different way of the quality and then feed water concentration. So in general, even though we follow this way, but you have to do pilot scale. So pilot scale operation, this will give very much good uh, your indication of how many stages would be ideal. So experimental oriented your decision making, or in general, like brackish water, different recovery rate, how much stage you need. So if you have a more recovery, you need more stages. So seawater desalination, what's the recovery rate depending on that? So also we need to look at the stage, how many stages in terms of element, 6, 7, 8. So we can also decide. So that's the how we can work from this tables. So it's like an experience. You have a you will know why we select this one. At this moment, you are based on the previous table information, but when you have several experience from the your water quality and the water membrane process, then you will get much more idea how you can decide your stadium. So that's the very good question. And then we can follow based on your experience, because you have no experience, so we can use a table. But if you have some experience of the RO operation, you will also design your own way of the staging. Of course, it doesn't have to be 2 stages. It's possible to make one stage. It's possible also make a 3 stages. So it's completely up to you, but based on the previous experience from others, the 2 stages would be ideal for you. But as I mentioned, you can make 1 stage, you can make 3 stages. It's up to you. Do you understand me?
Yeah, thanks.
That's good. Any other questions? So this is the very simple way of the calculation you can do from your hands. But when you increase your flow rate, like let's say Sydney desalination plant, you need to make more than like 10,000 cubic meter per day. You need a lot of pressure vessel, or you need a lot of element. So you need a lot of stage. So you need to design very differently, right? So in this case, you cannot use your hands. Also, you want to see the overall water fouling issues and the water quality issues and the water permeate quality. So you want to see detail. In this case, you have to go next step, which is wave computer program. So this is the wave computer program. So when you install your software, you will see this kind of first screen of your wave software. So how many people already installed your software so far? Everybody have any issue to install your software? Okay, looks like I can see your some. That's good. Sarah is okay. Olina is all right. And everybody hopefully successfully installed this software. Yep, that's good. Hala, Danish. And okay, so when you install your software, first let me try to explain, and then we can have an example together. So this is first screen. You have a feed water, what's the flow rate, the product water, how much you have, So in your assignment, you need to say how much you can design, and then you can have a 45% or 50% product water. So your water quality, you can decide. Also your pre-treatment, you can put just you drag, and then put it in front of arrow. You have here is also different pre-treatment. So you can select whatever you like in this process. And then you will have a feed water, reverse osmosis, summary report. So this will give you another level of your design for your seawater desalination plant. If you click the feed water, so you can see the stream 1, stream 2. Also, you have a different feed water, branded seawater, and a conventional pretreatment. And you have also ultrafiltration, what's the SDI value, so turbidity, TSS, organic content. So you can put also different cations, anions. So you will have a different concentration, and you have a boron concentration, CO2 as a neutral. So you put all the information as much as you can in your table of scenario for seawater, and then you may not have a balance of your cationic and anionic. So when you have some adjust cationic, adjust anionic, adjust all ion, because plus minus has to be well balanced. Otherwise, your water quality, something is missing. So in this case, this adjustment solid, you can click it, and then you will change the value a little bit. Also, adjustment pH, you have a pH 6 because you adjust your pH based on your initial feed water pretreatment. So you can change your pH and the temperature minimum, maybe in the morning, early morning, and in the maybe morning session, as well as in the midnight, daytime. So you have a very high temperature of your maximum. So you have a little bit of fluctuating your temperature. So you can put it as well as the pH. So in this case, you have a feed water is well balanced, and go for your some of the temperature. Why this is important? pH, why is important? Because pH and alkalinity, this is very much important for the scaling prediction. So this software will predict your scaling. So it's depending on your pH and alkalinity. So this one has more high pH, will have a more scaling potential. And the higher alkalinity concentration will have a more high alkalinity potential. Also, TDS influence RO operating pressure. So this is the RO operating condition. So you have osmotic pressure. So this is important. Also temperature, so you have a high temperature, will have a less viscosity. Then you less viscosity will which means you have a easy to permeate your water. So cold water will have a high viscosity, which means you are very difficult to push through your water molecule into your outer membrane. So when you have a 1 degree difference, your flux will be impacted almost 10%. So 1 degree will have a 10% different to your permeate flux. So temperature is also very important. Also inorganic calcium, sodium, barium, silica, bicarbonate, already we discussed during the water quality. Also SDI, we also discussed about this one because SDI has to be given by your software. And that's the feed water you need minimum to include in the software system. And then reverse osmosis. You have a second stage, first stage, third stage. So you have to also make it clear first pass, second pass. So this is the first pass, first stage. And this is the second pass, two stages. The second pass, two stages. And then they want to increase the recovery ratio. That's why we want to put the second stage at the second pass location. So this is the first pass, first stage. First pass, first stage. So if you click the pass two, this pass two will show second stage. And so you have to design initially your feeder is coming 750, 75,000 cubic meter per day coming. Recovery is 43%. Then permeate is 32 to 58 cubic meter per day goes to the second pass. So this will give almost average flux 16.5 LMA. Then permeate free flow is 9,677 cubic meter per day. So this will give this kind of information. And then if you click the second part, you will start your feeder flow is 332,000 cubic meter per day, and then goes to the next, and then you will recirculate. So that's the how you design. And then if you see the first part, how many pressure vessels you need, how many element you have. So you can select your element, your membrane, SW seawater 30 HR, high rejection 440. So you will also get your pre-stage pressure and then back pressure. And this is the how you can calculate from your system in RO. So you will have a rejection property, how you can get your membrane, how you can select your membrane. So in fact, you can select based on the manufacturer company, or this is the very general seawater desalination SW30HLLE440. So that's the you can select for your membrane. Also, manufacturing can often you can try to discuss together to select the different membrane, and then product water quality from RO will change as a function of the following: the feed quality, variable operating flux, and then process recovery. The list of the salt rejecting FIMTech membrane from Dow Chemical, the nanofiltration membrane, brackish water, seawater, SW, low energy, SWH, high rejection. So you can select from this basic information of your assignment. And this is also membrane selection criteria. So you can have a membrane selection TDS already. We briefly discussed about this one. So I will just skip. And each membrane element also they have a vessel has operate within the certain limit to minimize the concentration polarization and to avoid the physical damage, and using the RO software check for the flow rate per vessel in first stage, concentrate flow rate per vessel in last stage. So you need to also maintain this water balance. Otherwise, they don't have enough water for the feed water in the permeate flow, so that you will have a problem. So you have to make sure all the water based on your recovery. So you will achieve the individual element 8 to 14% of your calculation. So if you see this second pass, you have a second stage. Last one was the first pass. This time is second pass, second stage. So we have second stage 2 to 5, and then 203 permeate. So you have a 90% because your feed water is already filtered. So very low very high quality of water. The very pure water is coming to this one, and then you will get your own way of the permeate flux, so that you will achieve the 90% of your recovery. Then flux is 32.9 LMH. So you will get this one. And then concentration recycle flow is around 2,258 meter per day. You can decide. And then stage 1 here, stage 2 here, you can also calculate roughly your stage pressure vessel and the element for pressure vessel 7.7. So based on that, you can select your membrane, same membrane here, and then you will get also your design the results. Also, if you click your pH, adjust pH, so you can say your pH is around 6, and then how much H2SO4 you can incorporate before pH adjustment and after pH adjustment, after pH, and then how you can go for the RO plus concentrate pH. So your pH is keep increasing when you extract more water. Also, LSI value, it's very important because here red color, it shows your scaling potential. So if you see the red color in your report, the calcium phosphate in your RO path, you will have a problem. You will have also problem calcium chloride, magnesium hydroxide. So temperature, you can operate 28 degree. RO recovery, you can have also recovery 75%. So this is the way you can also look at how you can design your pH. Also degassing, also anti-scallant, also dechlorinator, which means SBS, you can incorporate. So you can also design your own way of the different chemical adjustment based on your red color, because you have a very red color, so you want to make sure your red color change to the black color. So if you see the LSI value, so as I mentioned, LSI value is 113.31. So this LSI value, if LSI value is more than 1 or 0, so you have a scaling can form. So positive greater than 0, scaling can form. So negative less than 0 is no scaling form. So you have to make sure your LSI value, Langelier saturation index. So because of the calcium carbonate, and calcium carbonate easily creates the problem. So you have to make LSI value is a negative. So you can see the steep value is negative, and then this is the positive. So if possible, you can make a negative to reduce your overall scaling issue. So based on your report of the wave program, so you will see, okay, I want to have a more negative value rather than positive for the calcium carbonate, because this LSI value is calculated by pH minus pHs. The pHs is here is -0.3 plus A. A is a TDS. So you have more high TDS will create the more fouling, because B value is your temperature. You have a more higher water temperature, you will also have a more higher potential. Also, calcium concentration is high. Also, you will create the much more higher calcium concentration potential. And then you have alkalinity is higher. Also, you have a more potential of the scaling. So based on this value, pH minus pHs, in terms of TDS, temperature, calcium, alkalinity concentration. So you can calculate what's the LSI value, and you don't have to worry because Wave software will automatically calculate this value in the system. And based on your all the adjustment of the chemical, you can summarize your report. So you have feed water pass one, pass two, then they recirculate, and then what's the uh, change of your flow rate, TDS pressure. So this report will show you very detailed of the overview. So what's the first stage, first pass, second stage, second pass. Then we have water type, seawater with membrane SDI less than 3, RO permeate less than 1 of the SDI. So we can see the total area, how much you need, what's the total number of elements you need, the total flow rate, pressure, flow factor is around 0.9. And then permeate water flux, average water flux, and the average and the specific energy we need around 6.15, which is not considered as a pressure exchanger. So you can consider pressure exchanger 50%, 60% based on your value. And you have 0.57 kilometer per day. And then we have temperature 8.6, 28.4, and then pH 8 and 9.7 after adjustment. And our system recovery 41.1%. And then that our system recovery 41%. The specific energy you need around 7 kilowatt hour per cubic meter, which means if you connect with the pressure exchanger, you may reduce the 50% of your overall energy consumption, which means you will get around 3.5 kilowatt hour per cubic meter, because this software has not considered your pressure exchanger. So you will get this report from your design system. Also, you will get the very detailed value, your membrane, how many pressure vessel, how many flow rate, recirculate, feed pressure, concentrate flow, pressure drop, permeate flow, average flow, permeate pressure, permeate TDS. Also, you have a detail your concentration. For example, like your sodium chloride concentration 14,000. After pH adjustment, same. Concentrate, you have 16,000. And then you have a permeate 37.68. So 68 milligram per liter. The sodium concentration, your permeate and concentrate is very different. And calcium storm was one of your assignment question is about boron. Boron concentration is almost 5. And then after your permeate, 0.55. So this is pass 1. So still 0.55. Then you have a little bit high concentration, so that you need to go second pass, and then you will have a better of your stage boron concentration can be reduced. Also pH, you can see how they keep changing. So you will have RO pass 1, your concentration. Also pass 2, you have similar information based on your pass 2. You can see the only boron concentration. It was 0.55, and then it was initial. This is second pass. The boron concentration is the final concentration is 0.26, which is the much better than first pass. So this is the very much threshold, less than threshold concentration of the boron. So which means you can get all the energy consumption and then different ions concentration change based on your selected RO membrane and then your operating condition. So this is also make a very detailed element 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So you have stage 1 and 2. Why they are changing the recovery rate? How they have a more different concentration flow, permeate flow, the permeate TDS. So you will get all the detail for each element, each stage concentration. Also, as I mentioned, we can see the RO solubility warning. So this report will show you also what's the warning of the your design. You have a stiff index is more than 0 at the pass, 1 pass. And then LSI value is more than 0, which means you have a still fouling potential. In the second pass, also you have a magnesium hydroxide, anti-scalant may be required, and consult your anti-scalant manufacturer. So they will also suggest that you have to do anti-scalant addition. You have to also change the pH. Also, you have to look at all the some warning from your report. Also, aerochemical adjustment, pH, and the LSI value, the stiff index. Also, you can see what could be the best way to respond this kind of problem. So that's the all about how you can utilize your wave software, and then we can try a little bit of exercise. If you turn on your software, this is the wave software, right? So let's make very simple. Okay, I want to do your seawater. Where is seawater? Yeah, water type, and I want to design RO. In fact, in the assignment 3, you may specifically targeting on RO for your software application. But if you design your system as ultrafiltration, you can put the UF. You are coming the feed flow first pretreatment ultrafiltration. Then you have ultrafiltration section. You can also change your parameters. Then reverse osmosis and feed water. And also if you want to make policing, so I need to change this is I need to change resin and mixed bag. And change mixed bag because still you don't like the very small ion compound in your RO permeate. So in this case, you can utilize the ion exchange resin to remove all the ions in your water permeate. Also, you have CCR, the closed circuit RO, which means when you have a very, very high recovery rate, so you can just keep rotating and then you will have a very high concentration of the RO system. So it's when you utilize the high recovery, the closed circular reverse osmosis can be used. But in your assignment, I don't think even you need an ion exchange membrane or resin. So just possibly, if you use the fuel media filter, yes, you don't need ultrafiltration. You just design RO because assignment RO question is this is the minimum. But if you want to select your ultrafiltration, it's better to you use the ultrafiltration as a pretreatment. And you can go one by one. What's the feed water? You can put all the value here, ability. You can put all the necessary value which already you know. And then ultrafiltration, you can design what's the automatic strain recovery, backwashing. So you will get all the necessary information in this ultrafiltration membrane. And then you will have okay, so I cannot go, yeah. This one is ultrafiltration and okay, so they're asking some concentration of the, maybe we can have this one. I selected one of the example file, seawater desalination. So you can see the 72,000 cubic meter per day, 30,000 cubic meter per day. So you have two different, almost 43% of the recovery. The ultrafiltration, yes, okay, let's put there at this moment. So we want to design ultrafiltration RO. And you will see the basic information of your water quality. The conventional water quality membrane. So here is the membrane pretreatment less than SDI 3. And then you can provide, yeah.
And the water subtypes, I have options different than yours. I have 4 options that are similar to the first one. And the feed water section,
Feed water section. Yeah.
yes. And the water subtype and feed parameters. Yes, second one.
Second one, yes.
Yes, I have different options.
Right, because you want to use the UF because we use now UF, right? DuPont. Or you can use the membrane pretreatment less than 3 or less than 2.5. So you can select here. But if you want to use conventional, which means the sand filtration.
I
like
mean,
Huh?
the system is giving me different options. I have NTU less than 5, TSS less than 5, TOC less than 2, and 3 others.
That one doesn't have the treatment options, just different NTU and TSS.
Yeah.
I see. Okay, because your version is a little bit updated version than me. That's why I think that's the same meaning. What's the NTU you have? What's the classification?
There's 5, 10, and less than 20 or larger or equal to 20.
So let's tell me that the NTU is less than 5 is the very good quality. And then 10 is the middle, maybe 20 is a little bit this conventional one. So depending on your NTU, or this is exactly similar, like your ultrafiltration pretreatment, you have a very low NTU, Then you have a, so that's the, you can select, of course, if you can measure the sample, that's the idea, but which means low NTU means you have a very good quality of the pretreatment.
Okay, thank you.
Does it mean if it's got low NTU, it means a low SDI as well?
Exactly, that's correct.
Yep.
Yeah, so which means the best quality of pretreatment, which say ultrafiltration. In this system, what we have SDI 2.5, Yupong UF, which is the exactly same. We can put the UF in this pretreatment system. That's the what we can do. Or like you have a microfiltration or some conventional one. Okay, oh, you have NTU here. Okay, seawater. Right, you have a seawater. Okay, we have seawater, we have softening water, we have wastewater. So depending on the, okay, NTU, right, QC less than 2. So which means we have a low value, we'll have a best water quality. So that you can select based on the your pretreatment system. Yep. And then you will get the good quality of pretreatment to RO system. So you can select that. And then this is the given typical seawater concentration. So you have almost 1729,000 milligram per liter, 7.6 milligram per liter. So TDS is around 46 milligram per 1,000 milligram per liter of your TDS concentration. So you have this kind of information, but if you try to push this one, so you can automatically can get all the adjustment of ion, because sometimes you measure your sample doesn't really give all the details, so that your balance is not exactly correct, so that you will have a very much different way of your calculation number. So you can put adjust all ion, then you can also put the adjustment pH. So you can also change the pH value, and ultrafiltration, reverse osmosis. So based on first pass, second pass. So you can see your design. First pass, we design 43%. And then you have permeable flow here, and you have a water flux 6.5. So you can calculate how much pressure buffer, how much element. Also, this is the membrane. So you have a different membrane, different also nanofiltration membrane. Even though this one I selected the seawater, that's why it shows only seawater. But if you select nanofiltration, so you will have a lot of nanofiltration membrane. This is all commercially available membrane from Dow Chemical. So you can select one of them, and then it will give us a good. The flow factor is the almost efficiency. So your flow efficiency is 0.9, 90%. So that you have like a very new membrane, you have a very good performance. So your efficiency is almost 90%. But when you use your membrane, 1 year, 2 years, 3 years later, your membrane performance deteriorate, and you will have a less performance, which means you will get the very, very low flow factors around 0.7, 0.8. So that's the how it can be calculated. So that's the what we are thinking about. And then second pass. Second pass is this one. So you can also calculate stage 1 and the second stage. So how many pressure vessels, how many element you need, and then different membrane. So this time is the brackish water membrane. So nanofiltration membrane was different types of membrane. You can see this is all commercial membrane. So you can see you can specify based on your experience, or you can ask to the manufacturing company which membrane would be good for your operation. But this is the brackish water, which means very low TDS. So I can select very much similar for BW30, maybe 400. So that's the how this works. And then you can click summary. The summary report will calculate how much water will pass through, how much you will get the energy consumption, how much you will create the rejection of the different ions, and what's your overall inorganic scaling potential, or some other pH adjustment, and some other your scalant. You have to anti-scalant has to be added. So you will get your calculating report based on that. So based on this one, so you will also go back. Okay, I got the owning of the design and how you can recover your owning, how you can design, and then you will get the also better way of the design. So that's the repetition. You have to continue to make a better design of your final report. So in your report of the assignment 3, so you can mention about how much element, how much pressure vessel, how much your final report. You can try to show in your assignment. That will be already good enough, so that you can also complete your assignment based on this one. I think this is a little bit long time. Let me.
Just Professor, I have a question. Do you have like an example that we can do to see if we put the data like properly? Because sometimes when we use like new softwares, we are not 100% sure if we put the data properly and give us the right results. So
Okay.
do you have any like example?
I have several examples. So one example, just the most simple example, I could say that. Okay, you can open your project here. So most general, our example, seawater. Yeah. So you can just open this one. So this will show basic information of your calculation as well, all the detail. So you can possibly change a little bit from here. That's the one example you can utilize this one. Specific element type pass 2 and stage 2. Pass 2, stage 2.
Professor, is the stage 1 and stage 2 information all calculated by wave?
Stage 1, stage 2.
Yeah, these parameters like pressure vessel per stage, and all of these, are they just given by automatically by wave?
No, there is no such automatic. You have to put the rough estimation. Let's say, okay, you calculate based on the initial our experience, based on your 720 cubic meter per day. You remember how many pressure vessel, how many?
Oh, yes, yes, sorry, yeah.
Yes.
Those are the like the
Okay,
simple initial
that-
calculations.
Yeah,
Yeah.
that's right. That's exactly starting point. Now we are going through, the initial was 75,000 cubic meter per day, so that this will have a much more value, so that you can roughly, estimate again based on your uh, proportional relationship with the simple calculation. And then you can put roughly your stage one, how many, and the stage two, how many, and then this is your first pass, the how many. So you need to roughly calculate and put the number, and then if you calculate in report, so you will get some value. And this value will tell you, okay, what is the wrong with your stage one and stage two or stage something. So this will give you a better design of your system.
How do you get
So,
the pressure parameters?
so you have to calculate roughly at the initial stage, and then you can try with your own way of the process. So if you try with our simple example, 720 cubic meter per day, based on our hand calculation, manual calculation, so you will get the rough idea how many you need, and you can include in the system. Because I don't know why it's a calculating report is why it's so long time to calculate.
Yes, Professor, I was trying to calculate the report for this example, and it says, please review your design. Yeah, it says wave has failed to converge. Please review your design.
Okay. Let me share with another one. Let me share. I will give now I will upload some other example, whether this is very strange because it's an internal example. It doesn't work, isn't it? Can you open other example from the inside examples file? I am trying to open. I will save can you go to plot 3 and example, wherever sample example, I will edit here. And then I will upload wave example. Mm. Super step. Yeah. This one. And can you download this to file whether it works better? Yeah, now you can download from the wave bus. We have some, because why it's calculating so long time? It's very interesting. Have you opened the my file?
Yeah, I'm trying now, Professor.
Okay, it should be working.
I got it.
You got it, right?
Yeah, the seawater example.
Right, that's correct. So this is the what I have another example I shared in the camp. So this is the based on the or can you see the my screen?
No.
No? Second, stop share. Let me share again. Can you see the my wave software? Yes. Can you see that, right?
Yes.
Okay, so this is the what I create the 4991. See what the wave example version 2. So this is the what I tried to get this one, and looks like this is going well. It's calculating, and then it shows the report what I expected. So I think from this example file, yep, you can change it slightly from your information in the assignment tree, and then you can make a fun to change your design parameters. Then ultrafiltration you can incorporate in the system. So you can change the sum of your design if you like, but I don't want to go for too much. At least the arrow you can handle from this program. That's the main objective of this software. If you really want to design with ultrafiltration, yes, that will be fantastic because you will have a better advanced ultrafiltration as a pretreatment arrow hybrid system you are designing. So this will be great. You can have a more experience. So that's what I suggest that you will get all the detailed information of this system. So do you have any other question for this software?
Professor, so if you go to the reverse osmosis tab, how did you calculate the pre-stage pressure and then the stage back pressure?
Okay,
All these pressures.
that's the very good question. Okay, can you see bigger? So how you calculate this one? Yeah.
Yeah,
That's
and also the boost and the feed pressure.
right. That's exactly based on your flow rate balance, and then feed and permeate. So which means, okay, sometimes if you put the pre-stage delta P, so this pre-stage delta P, if you click this one,
It didn't do anything when I clicked it.
of course, you don't have to do this one because what happens is that if you see the backstage pressure here, okay, let's say, let me put 0.1, you can see how this changed your backstage. Let me put the 0.1. So you can see what happened is that water is flowing, and then when you give a 0.1 back pressure, the water is not flowing against the 0.1 bar of your back pressure because you need to balance, because you want to give a more concentrate brine flow rate, because your balance of the permeate is too much. Yep, that's why reason you want to slow down your permeate. So in this case, you can utilize the back pressure a little bit, which will balance your concentrate flow goes to the next your step, and then next concentrate channel. So that's the reason why you are putting this one without. So you can remove your back pressure. It's the same, second part, you have a 0.2 as well as also it's also 0.2 and 0. So you have a 3 back pressure 3 bar. You give 3 bar because you have a very low TDS concentration. So your flow rate is too much, so that your water concentrate is not coming through enough. So your balance of the water is not good. That's what reason you try to control the back pressure here, and then let them concentrate the flow is going to the next step. Also, you can control this one. Also, what happened in the pre-stage delta P? Okay, what's the pre-stage delta P is you are coming, your water is flowing this way, right? And then you have a permeate water is passing through your also second stage, second pass, and then what happens is that you have a little bit of pressure. The pre-stage, your pressure will be around 0.2. So you're pushing through 0.2, pressure goes to in this system. So you have additional pressure of the, but if you give a 0, then if you give also this one 0, so you can see the report, how this will change, because you will have less 0.2 bar delta P, because this is automatically coming through, and then you can add your overall pressure plus your pre-stage pressure difference, so that you will get the additional pressure. But if you don't need that kind of pressure, yeah, you don't have to give. So you can try with all the three-stage pressure 0. Then what's your summary report? And then when you give a stage back pressure 3 bar or 2 bar, 1 bar, then what you change that could be changed your summary report. Like you can see the 1, 2, 3, 4, 5, 6, 7, 2, 8, 6, 8, 9. So you can see what's the pressure each area. You don't give a 69 bar, right? You don't set up, because automatically this is set by your computer software, because your membrane and your recovery rate, your flux will calculate this much of your pressure, net pressure. Then based on that, you can see when you have this pressure with your also system, so you can have a back pressure, you can have a delta P, pre-stage additional pressure you can consider, and then you will have a little bit of good flow. So when you have a flow rate, for example, feed flow rate, retentate flow rate, and the flow balance, flow table, RO flow table. So where you have a flow table here, feed flow, feed pressure, and then concentrate flow, permeate flow. So they are relevant to your applied pressure as well as back pressure. So if you are not really well designed, sometimes you don't have enough concentrate flow. Sometimes you don't have enough permeate flow. In this case, you can try to apply more pressure or delta P pressure or back pressure. You can control. So that's how you can change your overall operating parameters.
So those
That's
operating parameters, is that, do we just, have to determine that to suit the, required, permit flux?
That's a very good question. In fact, this pre-stage and stage back pressure, you don't have to worry about much, because if it is a set what you design, so you can utilize as it is and then show in the diagram. That's enough. And otherwise, uh, if you, in fact, you can put the all 0. You can put the all 0. Can set, even though they automatically change. Also, that's the possible scenario. Otherwise, you just show, as long as you have a summary report, what I concern is that design earnings. So when you click the summary report, so you will have your design report. So here in design report, this is the most important. Our design earning is nothing. So if you put the back pressure is too high, so you will get, you have too much back pressure in your flow, so you don't have enough permeate flow. Your design warning will show you. So as long as you don't have any design warning, so your system is well designed, even though a little bit of back pressure, a little bit of pre-stage pressure, it doesn't really affect overall your design warning. Do you understand me?
Yeah,
But if you set this way, okay, you want to design, that's exactly the experience from the real plant operation. So some people, they have that kind of operation to balance your back pressure and then pre-stage pressure utilized, and then calculate your overall water flux design. So it doesn't really matter whatever you put this value or not, as long as you have no RO design awning, so you're enough. But if you have something wrong, for example, let me change the, let's say 10. So let's see what's the design awning we would have. So when you have a wrong calculation of your pressure vessel, little bit of different flow rate, I think your summary report will show you something very different. That's why I like to see you look at your design owning of the RO process, and then as long as your design owning is none, that's the reasonable you have a design. Otherwise, this summer report, even it takes a very long time to calculate this kind of nonsense design system. That's why it takes sometimes when you have a very unreasonable value in your system, so it takes a long time to calculate. Also, it goes to the error message. So as long as you have a no auto design awning, check carefully, and then there's no design awning problem. Yeah, I'm happy to see your overall. And then this kind of small three-stage back pressure, it's a small technique, so you don't have to worry about too much. Yep.
Yeah, okay, thanks.
So that's why I changed this value.
It's
It
not gonna
doesn't-
work, it's
yeah.
not gonna work, there's not enough pressure vessels.
Exactly. That's what it is. It shows the not enough. That's why you have to start with small scale, which we already practiced with manually, and then go a little bit higher, also a little bit higher, and then calculate, and then that's you can get the more confidence of your design, because this is the one of example. So you can make your own simpler and then better design of your RO membrane systems. So it doesn't really, you cannot calculate this one, isn't it? So let me close this one. Okay, so any other question for this wave software? So I'm sure that already you have a very strong confidence to handle this kind of software, and then you can enjoy your computer game. So you can put your change and then put your different pre-treatment system, post-treatment, whatever you like, and then incorporate your web software in your assignment too. So you can utilize appendix in your figures and just screen capture, and then paste your report as well as your screen of the RO system design and feedwater design, and then you will have a very good outcome of your assignment 3. So that's you can try with your software. Anything else? Everybody is yeah.
Just one thing on assignment 3, if you can kindly give us an example, same as the first 2 assignments, because that was very helpful in knowing how to or how the report should look like.
Okay, let me show you again. So this is can you see my canvas?
Yes.
So if you go canvas module, and then block 3, I think I will share after class this one before. example. So can you go there? Wave software assessments 3 examples. So here is example M3, right? Can you
Yeah.
click here? So you can see the example. What's the paging design parameter he tried to achieve? What's the wave software he utilized to calculate? Then how this report shows. So it's available on the canvas. Yeah. So
Okay, thank you.
you can see what's the his report and how I commented on his report. Also, he tried to use appendix because this is the one of their own appendix of the software. So this is just one example. So you can think about how you can improve from your assignment 3.
Okay, thank you.
Okay. Hello.
Yes, thank you.
Hello, everybody. Can you hear me?
Yes, we can hear you.
Hello. Hello, everybody. Can you hear me?
Yes, Professor. We
Yes.
can hear you.
Okay. So yeah,
We can hear you.
okay. That's great. So now it's everything is done. So we completed all the necessary design practice, and then hopefully you can cover by yourself. So this is the just to enjoy like your software to change the parameters and then how you can make a better design. Also, you can see the some energy cost as well as the some removal of the different ions. So based on that, you can complete your assignment 3. So it takes time, but slow down, and then we will have a several consultation timing before your submission due. So you don't have to worry. And then I'm sure that at the end of the semester, a lot of people, they have a assignment due. So most of people, they ask extension at the last minute. So hopefully we have now 10 people here, and then we can just make sure you finish as soon as possible next couple of weeks, and then focus on your other assignment, and then don't delay. Otherwise, you'll be also mess up your assignment. This one, especially this one is the design. So whenever you have more time, you will get more good outcomes. So you please start from today and understand what's going on for your assignment, and then utilize your software very confidently, and we will organize our meeting maybe two times for the consultation, and we can finalize the assignment 3. Any more questions?
Yes, Professor. If we do some progress from today to tomorrow, like after the consultation of assignment 2, can we ask you some questions about this assignment? Just because I want to start like trying to calculate something with the software, but maybe we can like I just want to double check if I did it in the right way. It's okay?
That's fine. Anytime, you are very welcome. Just send the email first, and
Okay.
then you can ask the question as detailed as possible. And then if you need any a face-to-face or even just a Zoom meeting. So happy to organize and then we can discuss together. So please send the email for your appointment, and yeah, we will have a time to discuss together anytime, maybe even tomorrow and next week, even whenever you need.
Okay, okay. Thank you, Professor.
Anybody else? So how do you think about seawater desalination plant? As compared to the assignment 1 and 2, how do you feel, Sarah?
I think that will be a challenge, but it's also today was very, very interesting. So if this is a technology that we can apply even for future generation and for also all the water scarcity, will be great. So good.
That's correct, because of most of the consulting company like Jacob, they utilize this software to look at the overall estimation and then also design. So this is the real practical solution you are trying to achieve. It's not like a very low level. It's almost consulting level of your design. You are now is experienced. So I'm sure that that's the reason why it's complicated. It's very, depending on your design. Also, that's exactly how the open question, open design you can achieve and convince your customers. So just feel like, okay, this is your consulting design project, then make it sure like a real problem and real solution. And this will be make you very confident for your water and wastewater treatment design, any other process, because this is the most complicated water treatment process design so far, so that you will have a very simple one if you feel like any other different water treatment process, you can make sure that everything will be much, much easier than this design of the seawater desalination and wastewater reuse. Any other question for today? So I will upload this video, and maybe tomorrow, maybe early next week. So you can start, your assignment already. You have experience with me. What's the target, design parameter, how you can handle from A to Z your design the problem in the assignment 3. So you can start now, and you will save a lot of time at the end of this month. And please don't ask me extension, because so many assignments is together. I know that. I know every year I have a same issue with students. So you have 10 people here, so please finish as soon as possible. Then this will give you, much more, faster other assignment to finish this one first. So please again next 2 to 3 weeks to complete your assignment 3. So we will organize your consultation. Hopefully you can come and then have a more discussion together in the next couple of weeks. So if
Thank
you
you.
have, if you have no more questions, I will close the today lectures. And thank you for your journey for the last 3 to 4 months. That this is my great pleasure to have this advanced water and wastewater treatment. I wish you all the best. I'm sure that your assignment 1 was fantastic. Everybody did a very great job. I'm very happy to see all the great marks. Also, the second assignment 2, I'm sure that this will give you good marks. And mostly assignment 3, this is 35 marks. As long as you follow my instruction, and then you will get very high mark. So please I wish you all the good marks and that understand your design of the best water and wastewater treatment. Thank you, everybody, and good luck for your end of semester.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Take care.